All right, good afternoon, everybody. My name is Joe Wang. I'm a research scientist in Engineering Quantum Systems Group at MIT, led by Professor Will Oliver. So first of all, I want to thank the organizer of this conference for inviting me to this talk in this beautiful place. You know, it's a cloister winery, which probably would never happen in the US based on the federal funding. But we're happy to be here. Our group worked a lot on the superconducting quantum circuit, but today I'm going to focus on a particular field which we are very excited about, which is basically a hybrid superconducting circuit with van der Waals heterostructures, or 2D material. So the idea is the following. So we are interested in the material, or the condensed matter physics that we call quantum material, and we're interested to see if it is possible to implement some of this material for existing superconducting quantum technology so that we can come up with different type of qubit, different type of control, and so on. We could also turn around by using existing superconducting quantum technology to study these materials that we are interested using the, using some well-established techniques such as AC probing, coherent control, time domain control, and so on. So this is the topic I'm going to talk about today. To start with, so let me just briefly go through the introduction. I think many of the speakers today has already gone through. So basically, the superconducting qubit, or for example, the transmon, is called the artificial atom. So it's nothing but macroscopic devices made with electric elements such as Josephson junction, capacitors, and also sometimes inductors. So to read out the superconducting qubit, one relied on the very typical technique called circuit QED. So again, this is basically confining photons in a cavity that couples strongly to the superconducting qubit, as represented by the graph here. And by doing that, one can facilitate very strong photon matter coupling and also the hybridization between the qubit and the resonated state, so that one can actually read out the state or the characteristic of the qubit by observing the shift of the resonance in the resonator. And what is more interesting for this purpose is that we can actually, because of this property, we can actually take advantage of that by coupling, for example, some materials for creating novel superconducting qubit, or the other way around, we can couple the matters, the materials that we want to study in this setup for detection, okay? So the material that we're studying, as I told you, is a van der Waals material. So it's a family of the 2D material crystal that can be made by the typical stacking technique to create the so-called van der Waals heterostructure, okay? So the idea of this material is that so that you stack them in a way that preserve the integrity of the structure and the functionality of this material. And we're interested in this material in this context in particular because these families of material are multifunctional. You get all kinds of flavors of material that can basically build a whole device with it. And ideally, it's a defect-free layer crystal so that it's good for coherence. It can be epitaxially assembled, and so that you have pristine interfaces. And also something that comes handy is that it's compatible with the circuit QED architecture, which is a 2D. Okay, so just give you a few examples. Over the year, there are a lot of examples, demonstration of the coupling the superconducting circuit to van der Waals material. For example, the voltage tunable graphene transmon qubit that we demonstrated in 2018, which used the graphene Josephson junction as a nonlinear element so that we can achieve a transmon qubit that shows the typical graphene spectrum, but also have the coherent control with it. And the idea with this is fall in the family called the gate mon that allows one to control or tune the qubit frequency with the voltage. We can also study the dielectric laws and use some insulating material in the van der Waals family as to make the lump element devices. So in this example that we demonstrated is basically a transmon qubit using a heterostructure made with niobium dicyanide, hexachloroboron nitrogen, and niobium dicyanide. And the idea is to make a lump element parallel plate capacitor for the shunt capacitor of the superconducting qubit so that we can actually, in this first demonstration, we're able to demonstrate some decent coherence, but with a size that's 100 times smaller than the typical transmon qubit for each single qubit. And there are also a very interesting application using graphene Josephson junction to make parametric amplifier. And also, of course, for application and scaling, one needs to go to the wafer scale fabrication using some CVD growth material. Okay, so today, actually, I'm not going to talk about these previous work today, but I want to use one example or one project to show the two aspects of our interest, okay? So what I'm going to talk about for the rest of talk is to probe the kinetic inductance in van der Waals superconductor. The van der Waals superconductor I'm going to talk about include the magic angle twisted bilayer graphene, as well as one of the TMD superconductor, niobium diselenide. Okay, to start with, I think we heard a little bit about the magic angle twisted bilayer graphene. So basically, you have two pieces of graphene stacked one to each other, and then when the angle becomes smaller and smaller and reach the so-called magic angle, which is about 1.05 degree, the band structure of the two layer hybridizes, and it facilitates the flat band. So you can see that actually it just opened up the whole phase, different phase of a material, including superconducting, insulating, and metal state. And this is first demonstrated in Pablo's group in 2018. And this is very interesting because, for example, in particular, if you look at the phase diagram and compare that to that of a high TC superconductor, you can see that they share a lot of resemblance. For example, you could all see the insulating state that's flanked by the superconducting state in the phase diagram. And also, if you compare the energy scale of the superconducting gap and the Fermi level, they both fall in the so-called strong coupling regime. So therefore, it is reasonable to assume that understanding of the superconductivity in the MATBG may provide insight into superconductivity in other highly correlated systems. Okay, so that being said, I think it's still fair to say that the mechanism or the pairing symmetry of the MATBG or a similar system still remain at the forefront of the MATBG study. So, for example, we are curious about the nature of the superconductivity. Is it a nodal superconductor or it's a nodeless superconductor? And if it's a nodeless superconductor, what kind of symmetry does it assume? Okay, so this is something that people are still interested. And if you look at the theoretical study, you can see that basically all kinds of combination has been predicted so far. So recently, there's a STM study that shows a nodal behavior in the TBG and TTG. And we're interested in this question using a different approach. Okay? So what we want to study in particular is we want to probe the superfluid parameter for the pairing symmetry. So as you probably know, in the high TC superconducting community, the study of the penetration depth or the superfluid density is a very, as a function of temperature, is a very useful tool because the low energy quasi-particle spectrum is characteristic of the type of gap that you have. So you can see in this example, for example, the nodal superconductor has a linear dependence with the temperature, whereas the typical S-wave isotropic pairing has a kind of exponential dependence. However, for the 2D superconductor, van der Waals material in particular, most of the technique that has been used for this study is very difficult to apply. And this is due to very small size, very thin film, and very low carrier density. So it has been very challenging to apply these material, this technique that is usually developed to bulk material on the van der Waals superconductor, including MATBG. So to tackle this problem, we come up with the scheme to study this material by studying the kinetic inductance and the superfluid parameter in this material. So just to give brief introduction, so basically when you have an electric element subject to time-varying electronic excitation, the impedance of that comes as in two parts. One is the DC part that doesn't have any dependence on the frequency, and also there's a frequency-dependent frequency that's given by the capacitance and inductance. So for the inductance in this circuit is usually given by two parts. One is the geometric capacitance, and also the term called kinetic inductance. So the kinetic inductance is basically, you can regard it as an inertia of charge carrier in response to time-varying electric field. So in the superconductor, it can express as the function of the effective mass, and NS is the superfluid density, or the density of a Cooper pair, and it's also inverse proportional to the superfluid weight, or superfluid stiffness. So, so the kinetic inductance is actually pronounced in the superconductor in the microwave regime. So we want to use this advantage to study this material so that the DS or the NS can be accessible by the circuit QT technique that we just talked about. Okay, so the idea is very simple. So basically, this is the methodology we're taking. So basically, if you have a, if you have a piece of you have a piece of resonator whose frequency is given by the effective inductance and the capacitance that's coupled to the transmission line. And now, if we insert a piece of tunable material with a very high kinetic inductance, the total inductance will change as a function of backgate, and then we can observe the change of the frequency to extract the added kinetic inductance in this device. Okay, so that's so you can basically just observe the frequency shift, and then we can extract the kinetic inductance as a function of base voltage. So this is the device that we designed for the experiment. You can see that basically there's a transmission line coupled to two resonators, and this is an experimental resonator where we can actually put in our TBG devices. And each of the TBG devices is connected to three DC electrodes that allows us to do the 4-probe measurement. On one end is connected to the resonator, the microarray input, and also the other end is shunted to the ground. And also this whole device is placed on a metallic backgate so that we can tune the carrier density. So if you look into great detail, this is the device that allows us to do full DC and microwave characterization of the devices. And here we also add the LC filter that we actually adopt from the spin qubit community so that we can suppress the photon loss through this DC line from the cavity so that we can have decent quality factor to study the devices. Okay, so the first thing we do is very typical. We do the DC characterization to measure the resistance as a function of backgate or the filling factor, and you can see the typical behavior of the TBG where you have the charging neutrality point, the insulating state, and also the two superconductor region in both Hall dope and electron dope region. And this can be confirmed by the DC measurement that we see here so that we can extract the critical current of these devices. Then, after establishing this fact, we can apply the microwave tone to study it in the micro regime. So here, what I'm showing you is the S21, the transmission coefficient, measured through the transmission line as a function, again, with the backgate, okay? And the bright line here is basically corresponds to time resonance that we see in the S21 signal. And you can see that there are features that we can recognize very easily. The first one is these two arc. This basically, you can see this resonance with a frequency that change as a function of backgate. And actually, you can look at this picture here, the basic align with the superconducting region of the devices. And there are also some bright line that corresponds to the charging neutrality point and also the insulating state, okay? So how do we understand that? So these resonance doesn't have any gate dependence, okay? So I think without going into too much detail, what I want to say is we can actually model this device in a very simple lump element model based on the device geometry and also helped with microwave simulation. So what we are seeing here, this is the actual device that we are seeing, and then you can understand that it considers two parts of the device when the device is insulating. So first of all, we look at these resonance, and we know this device are insulating, so the bulk of the graphene is insulating, is a large resistor. However, we also need to consider that on the edges of devices, because we use titanium aluminum contact, so there's actually a small region close to the contact that are actually proximatized by the superconductivity of the aluminum contact. And that actually forms some kind of weak link and small superconductor that also contribute to the inductance of the devices. So therefore, we can model these devices as one resistor in parallel with another inductor that is shunting the entire microwave resonator. And we can actually perform the microwave simulation and actually reproduce exactly the frequency of these devices as a function of the proximatized inductance. And also we find that the change of the resistance doesn't shift the frequency at all, but it actually changes the quality factor of the resonator. And this is something expected for a standard parallel LR resonator. So you can see actually the more resistive it is, the brighter or the higher quality factor of the device or the resonance that we see. That is confirmed by this one. Now, if we move on, okay, so I'm going to skip this one just to convince you that the proximity effect is coming into the play. We actually build the same devices with natural bilayer graphene, and we also see the resonance at the Dirac point, but it can be strongly suppressed very quickly by applying a small perpendicular magnetic field. And this is much smaller than the critical field of all the other superconducting elements on the devices. So from this, we can actually extract how much contribution that we have in the conductance given by the proximity region. And this is actually consistent with previous study in the proximatized monolayer graphene. Now, let's move on. So now, if we turn the graphene into the superconductor, the bulk superconductor becomes the bulk TBG becomes a superconductor. No resistance, but very high inductance, as we assume. And the proximatized region remains because the Fermi level is pinned by the work function mismatch. So now the model becomes two inductor in parallel, shunting the resonator. Okay? And then by changing the value of the TBG, we can actually see the frequency shift corresponding to what we see in the data. So this gives us the idea how we can understand and think about these devices. And then, so the methodology is for each of the devices, we put in the resistance and we scan for the proximatized inductance, and then we set that, and then we can extract the kinetic inductance by comparing to the actual device that we measure. And from there, we can have a simulation, and also we can extrapolate, basically get the linear relation between the 1/L versus the frequency, okay? So from the frequency shift, we can actually extract the kinetic inductance given by the TBG region. And from typical standard microwave fitting, we can extract the resonance frequency and inductance as a function of the backgate for the entire superconducting dome for both hole dome and electron dome region. Okay, now we believe that we are able to see the kinetic inductance. Let's take a break and re-examine the system that we are studying. So we know that TBG can be superconducting, and we also know that in superconductivity, the electromagnetic response is captured by this London equation in the London gauge. So basically, it relates the critical current density with the vector potential with the superfluid stiffness, which is given by the superfluid density divided by the effective mass of the carrier. However, this brings up a very interesting question, which is we know that these devices are the flat band superconductor, and in a flat band system or a nearly flat band system, the effective mass become exceedingly large, and it actually diverge when you are at the flat band limit. So that would leads to the zero superfluid stiffness, which is in a very big contrast with the experimental fact. So to understand that, the new theoretical insight is required to understand what's happening in the superconductivity in the MATBG and similar system. So it turns out it's proposed that basically it has something to do with the quantum geometry in this flat band system. So the quantum geometry basically deals with the geometry in the quantum space. In the condensed matter system, it's typically the block function in the phase space. And the so-called quantum metric is something that we are interested here, is basically, you can think of it as a distance. It quantifies the distance or overlap between wave function in the phase space. In the MATBG, it has been predicted that the quantum geometric contribution is actually very significant, and it actually surpassed the conventional contribution at the magic angle. And also, to precisely describe the system, one actually needs to consider more than 4 bands taken into account. Okay? So here are some features of the quantum geometric contribution. So one is that it dominates at the magic angle for the MATBG, and because of interaction driven, the superfluid stiffness scales with the superconducting gap. And also, like I said, we need to take more because there are more bands that come into play that contribute to this quantum geometry. So like I said, we're able to measure the kinetic inductance, which is inverse related to the superfluid stiffness. So here what I'm showing you is a plot of the 2 superconducting dome of same devices for both electron and Hall region. And you can see that this is basically we plotted with respect to the normalized with the dimension. This is the superfluid stiffness of our devices as a function of carrier density. And here what I'm showing you is the TC of the device of 2 domes as a function of backgate. So here are a few features that we are seeing. So first of all, we see the dome shape of the superfluid stiffness. And also, you can see qualitatively the dome shape, or the TC also have a dome shape, you can say they kind of scale with the TC or the gap energy, which is expected for the interaction-driven superconductivity. And thirdly, we see that we actually plot the conventional contribution using the number from the literature based on Fermi liquid theory, and we can see that it's much greater in magnitude than the conventional contribution to the superfluid stiffness. And actually, the maximum value that we measure in the devices is very close to some theoretically predicted numbers. So they're both something around 1 to the power of 8, 1 over Henry. And I think Professor Loud is going to tell you more about this, because actually after measuring this, we take a look at their their fantastic paper last year, and we can see that it actually, so the quantum geometric superfluid stiffness looks very similar both qualitatively and even quantitatively compared to our devices. So we're very excited about it, and I believe Professor Lau will tell you more about this exciting results. Okay, so yeah, so we kind of believe that we have the measurement of the quantum geometric contribution based on the theoretical prediction and also previous experimental results in the MATBG. So we can now move on to study the perisymmetry of the devices. So like I said, the DS is, the superfluid stiffness is proportional to the inverse of kinetic inductance that we can measure directly, and is also connected to the superfluid density or the mass for any given gate voltage, okay? So we want to study the temperature dependence so that we can understand more about the perisymmetry. So typically, in an isotropic S-wave superconductor, the change of the superfluid density with respect to 0 temperature is basically takes like exponential dependence as a function of temperature. Whereas in anisotropic or nodal superconductor, it exhibits much stronger temperature dependence that usually follow or can be captured by this power law, that's T to the power of n. And actually, the number of n here can characterize what kind of superconductivity or it is. So typically, for the 2D superconductor, n equals to 1 corresponds to the clean point node, or n equals to 2 corresponds to dirty point node, like superconductor with high disorder. So we put this relation into our data, and we are trying to see how it behaves. So basically, what I'm showing you here and here are the frequency in the z-axis as a function of backgate and the temperature, okay? And you can see that when we go higher and higher in temperature, the frequency goes lower. And by fitting this data for each of the gate voltage, we can actually compare to the theory. So this is a power law fit that we tried to do. So you can see that the red dashed line here are based on the best fit using the isotropic S-wave model. Whereas the black dashed line that fits even better to our data corresponds to the exponent of 2.8. And we can see similar behavior in the electron hole doped region. So again, it deviates from the isotropic S-wave behavior, but it also shows a pretty significant exponent. So we can do this fitting for the entire devices, and you can see that pretty uniformly, our devices have the exponent that's way above n equals to 2. So from this data, we believe this is more close to a nodeless superconductor. Is there any question? Oh, okay, yeah. And we can do the same for other devices, and although the entire superconducting dome for both H-dope and E-dope region. Yes? Yep. Yes. That's a very good question. So actually, I should have mentioned, for all the data I'm showing you, all the data we use to fit, we already taken out the contribution from the aluminum and also the proximatized region, which behaves exactly like an isotropic S-wave, as expected. So that one we have already taken into account. This is a very good point, actually. And you can see that the contribution is much smaller than this device. Okay? All right. So now the temperature fitting suggests that we have a nodeless, a highly asymmetric gap. Yes?
Yeah, sorry, one question.
Yes.
So you measure the superfluid stiffness DS, right?
That's right, that's right.
To extract an S, you need to assign a value
So that's why we talk about the ds, not the ns, because it's all wrapped together. Yeah, because you're right. So the M effective can change from different gate point. So that's why this fit is actually proportional to the inverse of ds. So the ds is capture the overall effect of the change of ns and the MEFF. So that's why people tend to talk about ds rather than ns in the flat band system. Yeah. So at the beginning we thought it's ns, but we realized it's more accurate to talk about ds. Yeah. Okay. So we actually, we are curious by, so we know that it's unconventional superconductors, it's non-isotropic, but how anisotropic it is, this is something we are curious. So to test that, we actually put it into a more generalized or extended S-wave model, which take into account of the anisotropy and isotropy that's captured by this parameter here. So and it also have certain temperature dependence, and from there we can find the anisotropic parameter alpha, which is something typically around 0.5. Okay. So just to give you an idea, when alpha equals to 0, it's isotropic, and alpha equals to 1 is a nodal superconductor. So alpha equal to 0.5 gives you something like this. And I should note that here, this is just a cartoon to give you the idea, like how the gap can vary. But we are not assuming any rotational symmetry or degeneracy in this device, because actually this fitting is insensitive to like the order of the rotational symmetry. So this is just an idea. You can use 2 or 6 or whatever. Okay? But just to give you an idea, like how these things can change in the K-space, just to get it, to understand what we are seeing here. But overall, for both N-dope and H-dope, we have something about 0.5 and 0.4. So this is highly asymmetric. Okay? So with this device, I'm quickly go through this part. So we can also perform the DC bias current while measuring the microwave. So basically, the whole idea is you put in some mechanism that break the Cooper pair, and you see how it responds as a function of this thing. You can use it by thermal excitation. You can also inject some normal current that also break the superfluid. And with that, we can measure the change of the frequency as a function of DC bias current simultaneously. And for this, I actually like to show this because it actually shows the different capability given by the DC and AC probe. So for example, if you look at this one, and within the plus minus 50 nanoamp current, we actually see no change in the resistance because the DC basically just measures the shunting current going through the device. Whereas in the microwave measurement, we actually see within the same range a very significant change of the frequency. So that is because the microwave signal actually probed the entire superfluid condensate. And you can see that the change of the number of the superfluid is reflected in the signal. Okay? We can do the same with the microwave power, which is actually equivalent to through the microwave resonator. So here we see the quadratic dependence of the current, which is equivalent to the linear dependence of the microwave power because it's the square of the E. So basically, the message here is the current and the power dependence is well described by the Ginzburg-Landau theory. And also, typically for some nodal superconductor, there's a feature that people observe, which is the linear dependence on the DC current or the or equivalent to the microwave power. We did not observe that. But I want to note that it's not the linear dependence of the DC current is not necessarily a universally observed experimental feature of the nodal superconductor. You can see both in different types of superconductor. Okay, so just to wrap up, we demonstrated a hybrid superconducting circuit that allows us to probe the order parameters directly in the van der Waals superconductor with a DC and AC probe. And this is a low temperature. The typical base temperature is 10 millikelvin, and the effective on-chip temperature is about 41 millikelvin. A high quality factor set up with hopefully higher sensitivity than other technique. And we see features of quantum geometric effect manifested by the measured superfluid stiffness in the MATBG devices. And we see the temperature dependence and biodependence that indicate a highly isotropic but nodeless gap. Okay? And so here's the summary of the result, but the question remains, right? Because we know the STM or some other experiment, they show a nodal type of superconductor. So we need to ask ourselves, is it really nodeless? Okay? So there are two scenarios that we can consider. First one, it is indeed a nodeless and anisotropic gap. End of story. Second scenario, is it can be intrinsically nodal, but the nodes are lifted somehow by certain kind of mechanism, which need further explanation. So one possibility is actually the contribution of the quantum geometry, quantum geometry contribution to the DS, whose temperature dependence and its implication on the parent symmetry, to our knowledge, is not clear yet. So this requires further study in this direction. And also, one should also consider the disorder or inhomogeneity in the devices. Although we see the same behavior in 3 data sets that's agreed like quite uniformly. And also, for these TBG devices, intrinsically it has to be fairly clean. Otherwise, you cannot see the superconductivity in the first place. Okay, so how much do I have? 0, okay. I just want to give, if you allow me 1 minute, I just want to show you, we use the same setup to study other high kinetic inductance van der Waals material, which has a lot of application in superconducting quantum technology. So this is the application aspect of our talk, okay? So we use exactly the same circuit, but we coupled, encapsulated niobium diselenide superconductor with 1D edge contact that coupled to the resonator. And so this is a device. And with the same idea, you can shift the resonance frequency because of the contribution of kinetic inductance. And we study this material as a function of thickness. And you can see that when we go thinner and thinner, the kinetic inductance become larger and larger per square. And just put it into the context, we compare what we have measured so far to existing high kinetic superconductor, or sometimes people call superinductors. So you can see that we are kind of on par with some typical material in terms of the kinetic inductance per square. We are still far away from the granular aluminum, which is a very promising material. But you can see that we are only at 4 layer, or 4 nanometer right now. So if we can go further in the thickness, based on the simulation, it can reach pretty high for 2 layer or 1 layer. And of course, with that, it's actually inhumane to ask a student to exfoliate and make devices like that. So for that, we actually go through the CVD growth material from Professor Jinkong's group that allows us to use the 1-layer niobium diselenide that can grow partially or even fully on different substrates. So this is something that we're working on right now. So we are measuring the kinetic inductance of the CVD growth very thin film niobium diselenide. We're trying to make the resonator the same motivation as the previous speaker, to make very small footprint resonator. And we also want to make superconducting qubits, such as fluxonium, using this material. And of course, it can be made with into Josephson junction, or constriction junction, or quantum phase slip junction. So yeah, I convinced you that studying the van der Waals material can actually give you 2 flavors of a very interesting scientific field. There are some examples that we don't have time to talk about. I would be very happy to talk offline. So finally, I want to thank our team at both MIT campus and also the MIT Lincoln Lab for the fabrication and measurement support. And in particular, I want to thank people in this row. This is what we call the van der Waals team in our group that worked very hard and very diligently on this project. And finally, thank you for your attention. And I apologize for going over time.